Alright, welcome back everybody. In this video we are going to talk about section 8.13 of AP Calculus BC, the arc length of a smooth planar curve and distance traveled. Okay, so what's going to happen in this lesson? We're going to build a model to find the length of a smooth curve between two given points. And then we're going to use that to talk about distance traveled of objects. So basically in the past we've built integral models to find the area of a region or the volume of a solid, and the basic method that we use in those contexts is we try to separate them or subdivide them into an infinite number of infinitely small things. An infinite number of infinitely thin rectangles in order to find area, an infinite number of infinitely thin squares, triangles, rectangles, circles, whatever, to find volumes. So when we're trying to find the length of a curve, what we're going to do is we're going to subdivide the curve into an infinite number of very small lengths, and we're going to add those pieces together by using the integral. So let's take a look at what this looks like. So suppose we have this curve here, y equals f of x. How would we find the length of the curve y equals f of x between x equals a and x equals b? Well, what we'd like to do is we would like to take a small piece. And of course, I can only write so small on here. So I'm going to make it a little bit bigger for us to see what's going on. So suppose I'm finding the length of this piece right here. Okay, suppose I'm finding the length of that. Now we can treat that length as the hypotenuse of a right triangle. And then using the differentials that we've learned about in calculus, this side of the triangle is the change in x. It describes how much the x-coordinate of this point changed from this point to this point. And this dimension is dy. It described how much y changed as we moved from one point to the next. And therefore, the length of this particular piece is going to be the square root of dx squared plus dy squared. Now, we have these x equals a and x equals b. So in general, what we're trying to do is we're trying to sum up all of the values from a to b of these lengths. Now, if you remember, in all of our other models that we've built, we always had a differential that we needed in order to integrate this function. It represented the width of the rectangle, or it represented the thickness of the, disk or whatever. But in this one, we do not have that differential. So we need to do some algebraic manipulation on this in order to get it to be something that we can integrate. So we're going to take this formula right here, and we're going to turn it into something different so that we can use it to find the length of this arc. And since this function is in terms of x, we're going to want to integrate that in terms of x. So let's go ahead and we'll do that. We're starting with the integral from a to b of the square root of the quantity dx squared plus quantity dy squared. Okay, so I want a dx in this integral. So what I'm going to do is I'm going to put a dx over dx in here. And then, since I want this dx to be present, I'm going to absorb this dx into my already existing integrand. Okay, so let's manipulate that algebraically a little bit. This is equal to the integral from a to b of, and dx is equal to the square root of dx squared. So I can bring that over here with the formula that we have for the length. And now I have something where I have a differential, I have a dx, which this would be something then that I can integrate with respect to x. Still need to do a little bit more work here. the square root of something over the square root of something, algebraically I can turn that into the square root of the fraction. And so then I can split this up into two terms. Quantity dx squared over dx squared plus dy squared over dx squared. And then I can get to my final formula. Dx squared over dx squared is 1. And dy squared over dx squared, since they're both being raised to the second power, I can raise the whole thing to the second power and write this as a single fraction. And there's my formula for functions of the form y equals f of x. Because remember, a and b were the x coordinates of the endpoints of that curve. And so there you go. This is our formula. Oh, and then I dropped the dx. I talked about how I needed the dx, and then I dropped the dx there. There we go. That's our formula for the arc length of a smooth curve when we're working with a function of the form y equals f of x. What happens if we've got a function of y instead? Well, then we want to take this, and my limits of integration are going to be f of a and f of b. Okay. I guess since I used x equals f of y down here, I should use something else. Let's use, whoa, oh no, crash, we've had a crash. Sorry about that. Some technical difficulties. My presentation software crashed there. So we're back. Now we want to do the same thing to put this into form for functions of the form x equals f of y. And when we do that, we're going to treat our a and b here. You know what? Let's treat those as the y coordinates. These are a different a and b when we've got a function of the form there. So this is equal to the square root of dx squared plus dy squared. And we're going to bring in dy over dy. And then manipulate this algebraically, just like we did for the curves of the form y equals f of x. You know, this turns into square root of dx squared plus dy squared over square root of dy squared. And I hope you know where this is all going in the end. You know, this turns into the integral from a to b of square root of dx over dy squared plus dy over dy squared when we simplify all this stuff. And then the dy over dy is equal to 1. And so the formula for functions of the form x equals f of y looks like this. We're going to take dx dy squared plus 1. Take the square root of that with respect to y. So those are the two formulas that we're going to use here for curves of the form y equals f of x and curves of the form x equals f of y. We could take this arc length formula and really integrate with respect to any variable here, as long as we, you know, manipulate this in the same way. For instance, suppose I had curves in terms of an angle theta. You know, I could rewrite this as the integral from a to b of square root of dx d theta squared plus dy d theta squared with respect to theta. So I could put any variable in the denominators of these and put it as my differential and then integrate with respect to that variable to find the length of a smooth curve. Preview of coming attractions for those of you who well, maybe see that coming. We will eventually talk about curves like that. All right, let's look at example 1. We're supposed to find the length of the curve y equals x squared from x equals 1 to x equals 5. So in order to do that, we're going to use the integral from a to b of the square root of 1 plus dy dx quantity squared. Since we've got a function y equals a function of x. So first things first, I'm going to find dy dx. dy dx is equal to 2x. And so this is equal to the integral from 1 to 5 of the square root of 1 plus 2x, the quantity squared, with respect to x. And then I will find that integral on my calculator to give me the arc length. So I've got integral of the square root of 1 plus the quantity 2x, quantity squared. I guess you could have just, squared that out on your own without typing it in as such, from 1 to 5. And we find the arc length to be 24.395 for the length of this curve from x equals 1 to x equals 5. Okay, on to example 2. Find the length of the curve x equals e to the 2y from y equals 0.5 to y equals 2.2. So we've got everything as x is a function of y, limits of integration in terms of y. So I want to find dx dy here. Dx dy is equal to 2e to the 2y. And so I can set up my arc length formula. This is going to be the integral from 0.5 to 2.2 of the square root of 1 plus 2e to the 2y, quantity squared, with respect to y. And now I'm just going to go ahead and integrate that using my graphing calculator. And so we've got the integral of the square root of 1 plus quantity 2e to the 2y, close the exponent, close the quantity, square the quantity, close the radical with respect to y from 0.5 to 2.2. And that gives us our arc length, 78.777. 78.776, also acceptable. And there's the length of that curve from one endpoint to the other. All right, we'll come back for one more video on this unit. It'll be a slightly shorter video. We're just going to do a few examples of finding the arc length and distance, and then we are done with Unit 8. All right, see you next time I'm seeing you, and have a great rest of your day. Bye-bye, everybody.